Welcome to the fifth lecture of the course on non-traditional abrasive machining methods, and at present we are dealing with different problems of ultrasonic machining. We have dealt with problems of concentration, problems of workpiece hardness variation, etc., etc. So, in the fifth lecture, let us quickly move on through other aspects of ultrasonic machining. We have just now solved a problem on concentration, and after solving that, I am sure that you will feel interested to solve this particular corollary. This corollary is, how many days can the workers work per month if company works on break even basis? That means whatever it saves by reducing the concentration, it gives away to the workers. In my case, it came out to be something like 24.7 days. That means you reduce the abrasive concentration to such an amount that you save money enough to pay the workers for exactly those many days. Okay? That is, you reduce the abrasive concentration. For that, you require X number of days extra, and you also save money to pay the workers for X number of days. So, what is X in that case? You can try it out of interest and see whether it comes out to be 24.7. Okay. So, let us take this problem, another problem on another aspect of concentration. A student calculates the material removal rate in ultrasonic machining to be 5 millimeter cube per minute for a particular case when C is equal to 0.65, and he has used the following expression with which we are already conversant with. So, what is the important point to note? The important point to note is that he has calculated he has calculated ultrasonic machining material removal rate to be 5 millimeter cube per minute when concentration is 0.65. Okay. Now, what calculations has he made? That we do not know. We only know that his concentration is 0.65, and he has put in some other values so that it comes out to be 5 millimeter cubes per minute. However, when he does the experiment for the same case, so he is now doing the experiment. So, in the experiment he expects that yes, I should get 5 millimeters cube per minute, but when he does the experiment, he finds that due to settling down of abrasives at the bottom of the tank, this, when I have carried out experiments on ultrasonic machining, I have noticed this. The abrasives invariably, since they are having a specific gravity around 3, 3.1, 2.8, etc., they have a tendency to settle down in the tank unless you create a lot of turbulence. So, he finds that due to settling down of abrasives at the bottom of the tank, the concentration reduces with time as per the relation C is equal to 0.65 into e to the power minus t by 100. So, exponentially it decays, the concentration becomes less and less with time, where time is in seconds. If starting concentration at t is equal to 0 is C is equal to 0.65, find total material removal in the experiment in the first minute. So, we are still interested in the material removal rate for 1 minute. That means, the first minute after you just start the experiment, and the concentration is just 0.65 at that moment. After that, we are interested to find out how much is the material removal in 1 minute, in the first minute. What is the difference with the theoretical calculations? In the theoretical calculations, there is no decay of the concentration, no decay, but here there is decay, and we have to find out that what do you call it, find out how much will be the material removal rate, how much less will be the material removal rate. Let us try it out. So, in the relation we have, had there been no no reduction of concentration, then we would have resorted to the relation MRR is equal to K into C to the power 1/4. This we are just shortening up the other terms, K into C to the power 1/4. Hence, in the ordinary case, where C is constant with time, we can apply the known values which the student has used. 5/60, that means he has found out that in 1 minute the material removal rate is 5 millimeter cube. So, per second it is 5/60 is equal to K into 0.65 to the power 1/4. Straight cut calculation, from which we can find out the value of K to be 5 divided by 60 into 0.65 to the power 0.25, e to the power 0.25. However, up till this point it is all right, but now we have a look at reality where C is changing with time, and therefore we bring in the idea of calculus. That is, if we define material removal rate as limit of dt tending towards 0 dm dt, I hope you can read the small script on the screen. Dm dt is equal to K into C to the power 1/4, so that instantaneously we can write that it is equal to 5 divided by, that is basically we are putting in the value of K now. This is the value of K. This is the value of K, and this is 0.65 into e to the power minus t by 100 into 0.25. Now, what is this part? This part is nothing but the instantaneous value of concentration. So, at any point in time t, okay, dm dt, which basically means the material removal rate, it is equal to constant. I have written the value of the constant, and this is the value of the instantaneous concentration as a function of t. So, instantaneously, this is always valid. Instantaneously at some point in time, it is a function of time. So, now what we do is, if dm dt is known to be this value, let us find out what it contains. This is a constant term, we do not have to bother about it. This is also a constant term, but we have a problem with this one, e to the power minus t by 400, that is 0.25. Now, it is brought inside, it is t by 400. Now, what do we do with that? So, we will be integrating to find out the total material which is removed over the first minute. So, we integrate 0 to 60, and this is the constant, etc., etc. Now comes the e to the power term, and therefore, after we integrate it, we get this particular expression. We apply the initial condition that at t equal to 0, okay, at t equal to 0, the value of concentration is 0.65, and there is no material which is removed at that time, and we apply we are given two limits. So, we apply that definite integral, and therefore, this constant comes out. Okay. Let us see what we have done. Okay, 60 into 0.65, 0.25, 5. This part is all right, and this minus 400 has come out here, and e to the power t by 400 has remained here, and this constant has remained here. Fine. Straight away, integration of exponential function has been done, and therefore, I have forgotten to write down the limits here. We apply the limits, and these are the two limits, and therefore, we get 400 into 5 by 60 multiplied by 1 minus e to the power minus 60 by 400. Okay. This one is going to be 1, and therefore, it is simply 1 minus, this comes forward and this goes back, and this is the final expression. Okay. So, instead of 5 millimeter cube, the material removed is 4.643 millimeters cube in the first minute, due to reduction of concentration in an exponential manner with time. Now let's have a problem on normal load, and this is in the MCQ form. Let's see what it says. A company makes glass mementos. 400 pieces of glass mementos have to be delivered exactly 10 days after receiving the purchase order. Now, do we have systems like that? Yes. If you cannot deliver within, say, 10 days, your order is cancelled. But what about those workers in that particular problem? Well, it varies from problem to problem. So, in this problem, it's 10 days or it's cancellation of order. The machine has two static load options. Okay. So, in this machine, you can either put 5 newtons or you can put 10 newtons. Now, is it a realistic case? Yes, it is. Discrete values can be applied. Like if you are having dead weight, maybe you have 5 Newton load and 10 Newton load, just like that. With machine overheads of rupees 100 and rupees 150 per hour respectively for the two. Now, if you are interested in applying higher load, maybe you will be incurring more current loss, I mean current consumption, etc., etc. And for that, the machine overheads are different. Higher load, higher pay. The part can be done in 30 minutes by applying 5 newtons. So, if 5 newtons are applied, okay, the work can be done in 30 minutes. That is provided. This information will be very useful. There are 2 shifts per day of 8 hours each. Only one machine is there. So, what is the problem? The problem is the time required for completing the part with static load of 10 is nearest to this 10 minutes, 20 minutes, 24 minutes and 18 minutes. Now, you might say first, because many of my students do that, I also used to do this. How is it going to be done? Or what am I supposed to do? So, let us see first of all what is provided. 30 minutes for applying 5 newtons. So, immediately we can say, I know that MRR is related to the applied static load. In what way? We can say MRR is equal to K into F to the power 3/4. So, immediately I have a starting point. I can say I can relate MRR to the to the load, and that way I can also find out what will be the MRR for 10 newtons. So, let us quickly do that. So, the first part says if M is the material to be removed per part, okay, M is the total amount of material. It has to be removed in order that the part is finished. So, what we say is if M is the material to be removed, therefore, material removal rate must be M by T, where T is the time required. That is good. So, M by T must be equal to K into F to the power 3/4. If that be so, we apply the case in which we are using a load of 5 newtons. So, the total material by 30 minutes. Oh, we are working in minutes. Okay. If we are always sticking to minutes, I hope it won't matter. M by 30 is equal to K into 5 to the power 3/4 for the case where F is equal to 5 newtons, and therefore, you can find out a value of K. The value of K can be found out this way, M by 30 into 5 to the power 3/4. So, if F is changing, okay, constant cannot change, K cannot change, and therefore, M is going to change, okay, or T is going to change. M cannot change. I am sorry, M cannot change, K cannot change, only T can change, and therefore, we put in the place of F we put 10 here. In the place of K we put its known value, and we have M by T on this side. So, that M and M will cancel out, and we will have a value of T equal to 5.75 divided by 10 to the power 0.75, and this is multiplied by 30, and therefore, we have a value, straight cut answer is 17.838. Okay. So, this is understood, not very difficult. Let us have a quick look. 10 minutes, 20 minutes, 24 minutes, 18 minutes. This is the nearest one. Have we mentioned? Yes, is nearest. Time required for completing the part with static load 10 newtons is nearest to. So, the correct answer is 18 minutes. In order to complete the part exactly on schedule, the machine should be run with static load 5 newtons and 10 newtons for the times nearest to respectively per part. Now, what does this mean? This means that if I am using it with 5 newtons load, I cannot finish it by 10 days. If I am using it with 10 newtons load, I can finish it before 10 days are over. So, you will say, what's wrong with that? Finish it before 10 days, have fun for the rest of the days, and then deliver at the end of 10 days. The problem is, if you do that, perhaps you are going to incur more costs. I have not checked it, but common sense tells me if you are using a costly facility, 150 per hour, definitely ultimately your costs will be higher. So, maybe you have hired the machine, you have taken it on a contract that I will use it for 10 days, and then you are trying to reduce your costs by utilizing the 5 Newton facility to the maximum, but 10 days is the limit. So, let us see how it can be done. So, what is the question? In order to complete the parts exactly on schedule, the machine should be run with static load 5 newtons and 10 newtons for the times nearest to respectively per part 15 minutes and 9 minutes, 9 minutes and 15 minutes, 12 minutes and 12 minutes. So, let us see what the answer is. So, first of all, we assume that let the times be x and y for 5 newtons and 10 newtons. So, x plus y, I can tell you exactly what it is, because I know that I have 10 days of work in my hand, and therefore 10 days will mean 2 shifts, 10 into 2, 8 hours into 8, and that multiplied by 60 will give me the total number of minutes. This I divide by the number of parts to be made, 400, and I get 24 minutes per part. So, that means by hook, crook or fluke, you have to get 24 minutes allotted to every part that you are making. That is good. So, per part, let M1 amount of material be removed, per part let M1 amount of material be removed by 5 newtons application, and M2 amount of material be removed by 10 newtons application. So, that M1 plus M2 is equal to M, that we know for sure, and we can also say M1 divided by X. Let me just point it out. M1 divided by X must be equal to M by 30, because it must be proportional. If you are spending 100 rupees to buy, say 4 cricket balls, then you must be spending 25 rupees to buy 1 cricket ball. So, if you are removing M1 amount of material for X amount of time, it must be proportional to M amount of material having been removed in 30 minutes of time. Same thing with M2. So, M1 by X is equal to M by 30, and M2 by Y is equal to M by 17.838. Remember, this is the value of time. Having understood this, first of all, M1 plus M2 must be equal to M, and therefore, we add up M1 by X plus M2 by X, M2 by Y. What do we do exactly? M1 plus M2 is equal to M, and therefore, we find out the values of M1 and M2 and add them up and equate it to M. What is M1 equal to? M1 is equal to M into X by 30. So, we write here M into X by 30. And what is M2 equal to? M2 is equal to M into Y by 17.838. M into Y by 17.838. Their sum must be equal to M. That is good, because M cancels out. Okay. You will find in mathematics, equations, etc., cancellation will always make you happy, because things are becoming simpler, and in our case it is X by 30, M has gone out, and in case of Y, okay, which was left, we have written it to be 24 minus X, so that yet another term is gone. 24 minus x divided by 17.838 must be equal to 1. And from this we can draw up one solution so that x comes to be nearest to 15 and y comes to be nearest to 9. Okay. From here you can solve for x, and then you can go and find out y by using this equation, and they come to be x is nearest to 15 and y is nearest to 9. This you can definitely solve from here and find out. So, this option is correct. Now comes a question on work material. Did we do a question on work material? Yes, we did. We did do that, but maybe it was connected with work material hardness. Let's see what this has to say. You are making and selling a USM machine mementos. Okay, USM machined mementos are being sold on imported glass. When price of imported glass samples becomes rupees 400 from rupees 200 each. So, wait a minute, there is a price rise which always makes you nervous. There is a price rise, imported glass has become of double the cost, and therefore, you were making small mementos. Okay, you have the following options before you. So, some sort of design was being ultrasonically machined on top of them. You can use Indian make glass samples, they can also be used, and they are cheaper, in fact, rupees 250, and keep the machining the same, rupees 300 per sample. What is the meaning of this one? Keep the machining the same. It means that you are basically keeping everything the same, all the conditions are kept the same. Or you can go for the imported glass. Now, why should you go for the imported glass? Because some people like them more than Indian made glass. You cannot control everyone. If someone likes it, that's it, they will try to buy imported glass. So, if you're in a business, you have to see whether you can make profits by selling them imported glass mementos. So, you have the option that you can use imported glass and double the dead weight, defining the static load. So, you are doubling the dead weight, that is the difference. So, the rate of machining will rise, but what do you gain for that? If man machine hour rate and abrasive cost per hour are rupees 200 and rupees 400 respectively, so it means that static load increase in this particular problem is not incurring extra cost. It is not incurring extra cost. Okay. So, that is good. Note that imported and Indian, that means desi glasses, have same properties. So, they will have the same hardness. So, in that case, the 4 options which are given is that A makes saving of around rupees 28 over B, B makes a saving of around rupees 28 over A, both the methods would cost roughly the same, etc., etc., and A saves around rupees 90 compared to B. So, let us quickly note what is the difference in the two cases. Simply in one case you are having double the load, okay, double the static load, everything else is the same. So, you have to be alert about the costs which are different and quite complex because they have changed over time, overnight. So, let us see how it is solved. Oh, wait a minute, I am sorry, I think what has happened is I have set this as a practice problem, take home assignment, okay, because if we solve all the problems in the class, you wouldn't be having any problem to solve for yourself when you want to make some preparation. So, with that in mind, I had included some problems which you can solve yourself, and you can intimate to me your correct answer, and then you will understand whether you have done it correctly or not. So this problem is, take home assignment. Acha, let me see quickly. Yes, this is also a sort of take home assignment, because take home assignments only will be increasing your confidence on yourselves. But I have given you a hint how this is to be done. You are using, so this is on abrasive. So we are covering different aspects, work material, normal load, concentration, etc., etc. And now come the abrasives. You are using one USM for die sinking up to a depth of 5 millimeters as per customer's order. Okay, so the customer has ordered 5 millimeters depth in a particular part. That's good. Using abrasive A of the list. Where is the list? It's in the next page. However, the customer changes the order so that the new depth is 7 millimeters. Okay, so the problem is understood. 5 millimeters of depth was recommended first, and then it's 7 millimeters of depth in the second case. But he wants it to be completed in the same time. That's the difference now. That means I want a difference, I want higher depth, but I want it to be done in the same time. So somehow you have to speed up the rate of machining. Okay. So if the rate of machining has to be increased, you can only use the abrasives in the list. If you can only use the abrasives in the list, which abrasive would be the most appropriate? Assume the same volume of slurry to be used up in all the cases. So the abrasive slurry volume is the same. That means if you are using 5 liters, you are using 5 liters in all the cases. So there is the list. Let's see. You are using at present abrasive A. What is abrasive A? Abrasive A says that the rho, that means density, is 3 grams per cc, hardness is 2500. Hardness of what? Hardness of abrasive. Average grit size in microns is 30, 41, etc. Price per kg is rupees 500. What's price per kg? Of the abrasives. And C is concentration. Sorry, C is the concentration, which is different for the different abrasives. But how is C specified? If I add more water, that will be, changing the concentration, reducing it. So it's recommended that you use this particular concentration for these abrasives respectively. If you are using first one, 0.7, like that. So in this case, it's a take home assignment, and you have to choose which one abrasive will give you 7 millimeters depth in the same time as 5 millimeters previously. So hints to the answer. The basic step that you have to follow is that MRR is changing such that MRR2 by MRR1 is equal to 1.4. And for the case of MRR1, abrasive 1A has been used, and hence simply find out the ratios of the MRR values using abrasives B, C or D, which satisfies this particular MRR ratio. Okay, so go on finding out which abrasive is fulfilling it. Since other parameters remain the same, only consider grit, size and concentration. That's interesting. Only grit, size and concentration are the ones which are listed in that table. They are going to affect this particular process. Maybe more than one will match the technical requirement of 7:5. Suppose you find 7:5, more than one they are matching. In that case, what do? In that case, you go and look at the costs, because as an engineer, you are expected to understand that you have to go for the cheapest one. Okay. How do you compare? We can check the concentration used. The same volume of slurry is used in all cases, and that way find out the volume of abrasives that would be required. As the density is given, find out the weight of such abrasives that would be used and multiply with the price per kg and compare. And my students told me that the last one is the correct choice. Okay. So, please do it yourselves, and after the first week of lectures are over, then I will share the answer with you. This is a take home assignment. There I will share the answer with you. In the meantime, if some of you you have solved the problem, you can send me the answer and I can check it up and tell you whether it's correct or not. Thank you very much.